so the base case, right? The one we developed yesterday for case one, that's what we're using here as an example. So let's just go over the project requirements here. So if you recall, yesterday we developed a usage profile for case one that was about at 1 megawatt, 4 megawatt hours. Here we're putting kind of some additional project requirements to put things in context. We're assuming we're designing for a 20-year project life with the requirement that the capacity we're designing be maintained throughout the project life, which is the most abundant requirement out there in development and design of energy storage projects. So what we do know is the battery usage profile here, right? That's what we did yesterday. What we do not know is anything about the system that we will deploy to execute that profile, right? What's here is green is known. What's in everything inside the orange box here is not known. Okay, so let's pull up Storlytics here. So the first thing we'll do is select the POI profile from yesterday. It should show up in your dropdown, and it should be called Case 1, Solar Plus Storage. And then for the TMY3 profile, we'll select the one for Sacramento, since we know this project is in Sacramento, California. All right, and now going to the equipment models. For this first design, we're going to assume kind of the most abundant currently, which is lithium LFP. So right now we'll select the generic LFP model. Right? We could have, in more kind of detailed design methodologies, you can kind of select actual products that are out there rather than a generic model. But if you don't have kind of OEM models, a generic model gives you a good indication of how the specific chemistry would work. Right, and then for the enclosure, what we were using here. Generic enclosure, air, LFP. Generic liquid or air? Okay, yeah, generic air, LFP. Generic air, steel, LFP. Got it. All right. Then for the inverter, we're using here a Sungrow 1 megawatt inverter. Since it's a 1 megawatt project, so let's go with Sungrow. And the 1_24, that's kind of the latest version of that model. So we made sure to include under the general tab for all models, under model description, kind of where it came from, or the source. So every the author of different models could be clear. All right. System specifications. Now this is where we get into system sizing, right? So here we're going to put 4 modules in series per rack and 26 racks per inverter, and 26. And as we're doing this, right, you can click here, calculate energy and power requirement. And this gives you kind of the 100th percentile of the usage profile. So it tells you the maximum discharge power in your usage profile was 1.1 megawatt. The maximum charge power was also 1.1. And maximum energy for both discharge and charge, it gives you those values as well. But again, these are maximum values, so the 100th percentile. Yesterday, we went over the histograms, and we kind of understand that, yeah, you could probably get away with a much smaller capacity, since these maximum quantities are just used not so abundantly. Right? So for the number of inverters here, we'll select 1. And as we're filling out these numbers, you'll notice here kind of the full or the design capacity is updated. So now I see that the system we've designed, total inverter capacity is 1.1 megawatt, and battery energy capacity at battery terminals is 4.8 megawatt hours. Right? For medium voltage transformer losses, both copper and core losses, we can just use the typical values, right, which is 1% and 0.1%. And here, we can fill in site constant aux load. So this is stuff like your control load, right? Your data acquisition system, SCADA, things that are always kind of operational. So here, what you see in this figure is the system topology, right? What's in green here are the battery modules. So each battery module has a number of battery cells in parallel and in series, right? Under the equipment tab here, if we open up any battery model, right, we can actually get to the cell level, right? So here we can know that for this module, right, there's 52 cells in series and 1 in parallel. So basically you have 52 cells all connected in series, right? So now for the module level, we stack modules on top of each other to form a battery rack, right? And then we parallel battery racks to form basically the BESS, right? And that's what we're kind of filling out here. So when we say here 4, that means there's 4 of these green modules, right? And we say here 26 means there's 26 battery racks in parallel. So it depends on the product, but for the most part, for utility scale systems, it's not kind of an off-the-shelf solution, right? You could, depending on your use case, right, you may need a duration different from the typical products that are out there. So in this case, we're a 4-hour system. So you may find products that are suited towards that. But again, 4 hours executing what kind of use case, right? And project life affects that as well. So it's very easy to go a non-typical route. Like, so OEMs will have products that are, 4 hours, 1 cycle per day, 10-year project life. So it's really preset for you, not very suitable for kind of utility scale, larger projects. Yep. So the site auxiliary load here, site constant aux load, it's called constant to emphasize that it's basically a value that the user would put to just get added as a constant for the simulation. You can use that to account for SCADA load, control kind of room load if you wanted to, but the cooling and the temperature regulation is calculated through this calc enclosure temp regulation aux load, right? Because that's not constant. That varies based on ambient temperature. It also varies based on your usage profile, right? So the higher C rate, the more heat the cells exert, the more cooling you need. So there's a very sophisticated model in the background converting from real-time C rate in the simulation and ambient temperature to real-time auxiliary load consumption, right? And that's separate from the constant load. All right. Okay, so we put in the medium voltage transformer loss values, site constant aux load. For simplicity, we'll just assume that's 0 for now. And here, as mentioned, we'll allow the software to calculate enclosure temperature regulation load, which is, let's say, more than 95% of auxiliary load on site, right? So really, really important. And then here you have the ability to kind of source auxiliary load from a separate feed, right? So when I turn this on, now auxiliary load in this diagram is connected to the grid, but from a separate point of interconnect other than the projects. If I turn it on or off, rather, now auxiliary load is being fed from the same point of interconnect of the project, right? So it really depends on your case. I know Duke Energy, for most projects, you're kind of sourcing aux load from the POI, right? You don't have a separate service. But for a lot of other utilities and companies, they assume that they're getting a separate service for aux load, right? So you can do it a lot of different ways, and this feature allows you to account for that. Operation, right? So here we touched on this a little bit yesterday, but you get to set the maximum state of charge you want your system to operate at. Yesterday, when we were kind of building the profile, we assumed it would be a 90% depth of discharge. So here you can set it to 95 and 5% maximum minimum state of charge. All right. And for the initial state of charge, we can set it here at 5%. Now, the reason I set it here for 5% is because I know the first day of this simulation is going to be one where we want to charge from solar, right, in order to discharge that energy later, right? So setting it to 5% here, right? And then battery degradation, we can turn it on or off by ticking this checkbox. So for the initial state of health, I'm going to assume it's 1, right, which is 100%. So basically means your battery cells are new. If you were trying to simulate a case for augmentation, for example, this is where you can kind of change this parameter and assume kind of the batteries have some life on them. So you would go, less than 1 here. All right, year life, we said the project is a 20-year project life, so we're going to simulate 20 years worth of battery degradation. All right, and here, going to name our project base case. For now, let's turn off kind of daily state of charge steer, right? And click run. Right. Let's make sure we save base case. Right. And then generate report. Okay. Now we can come back here. So we finish these steps. And I can also open this report. All right. So the report starts off with the inputs we provided in the battery system modeler, right? So we're not going to go over that. We talked about these models and these inputs, so we're good there. All right, and here, the first thing we see is a chart on achievement of power set points, right? Now, based on what we discussed yesterday, we expect not to achieve 100% of the set points because, it was highly kind of peaky and we were getting diminishing returns, right? So as we can see here for the power, right? And let me kind of back up a little bit. So what you see here on the x-axis is each point in the project, right? For both charge and discharge. So you have PY charge. So you have PY charge, inverter charge, battery charge. And Hoimin, to the point that you mentioned, right? Where are battery losses? This is where battery losses apply between the battery charge and internal to the battery. So internal to the battery is kind of like an ideal battery, right? All right, and then you have internal bat discharge, and then bat discharge, inverter discharge, PY discharge, right? So if we take an example and we look at the PY discharge here in blue, it's at 1100 kW. That means the maximum power set point for discharging in the profile you provided was 1100 kW. Us being at here 1060 kW here with the achieved means kind of we weren't able to achieve that at the PY, which is fine because, I mean, this doesn't happen pretty often during the simulation, right? Same applies for charging as well. All right. So let's shift to the energy achievement diagram here. So here, same concept. Every point in the project is laid out on the x-axis for both charge and discharge. So we see kind of in terms of throughput, megawatt hours, how much was required over the simulation and how much was achieved, right? And we can see here there's kind of a delta between, on the charging side, between what was required, or a larger delta compared to discharge, between what was required and what was achieved, right? So later on in the report, we can understand why that is happening, right? Okay, so here, this radar chart basically just summarizes the past two charts. So for both power and energy, it tells you how much was achieved at every point in the project, at the POI, inverter, battery, for both charge and discharge. And we can see here kind of we're at what you would call acceptable limits, recognizing that we undersized the system, as again, diminishing returns, right? So we know the system we designed here is going to be highly utilized and not oversized and be underutilized. So just as an example, if we doubled the inverter capacity and perhaps doubled the energy capacity we designed here, this would all be 100%. We may be happy, but really our financials are not going to look so good. So here, kind of this chart kind of tells you where the energy is going. And well, I should state that differently. What is preventing you from getting 100% everywhere here? So what are the capacity limitations, right? So 97.75% of the time, POI energy achieved. But when it's not achieved, we see 3.8% of the time we had a maximum state of charge limit, limiting us from charging. So remember when he said, yeah, this delta is bigger here, right, for the charge side, right? Now we know why that's happening, right? We're hitting our state of charge maximum a good deal. Well, just 3.8% of the time. So if we jump to the state of charge chart, right, and this is, I know it looks busy, but just to explain what's happening here, each of these bars, right, each of these bars represent for each day the maximum and minimum state of charge, right? The red dot represents the average state of charge for that day, right? So if we take an example here and we look at kind of, day 18, I know my minimum was about 20%, maximum state of charge 95%, right? And the average was about 45%. So as I can see here, see that a lot of the days I'm hitting the 95% upper bound of my state of charge range. So now this further kind of explains, right, this 3.8%. All right. Yeah, here you kind of lay out the overall charge efficiency, the discharge efficiency, and the resulting, round trip efficiency for your system, right? And then you kind of get some detail about where the majority of those losses are going, right? So here over the simulation, see 24 megawatt hours kind of provided for temperature regulation for the enclosure. So basically HVAC load for your battery enclosures. Inverter standby losses, right? So your inverters have fans and other kind of auxiliary load in them. So that's came to 149 kWh. Site fixed load, we set that as 0, so that's 0. And then enclosure fixed, this is kind of enclosure fans, control load, right? Because you have a lot of kind of equipment within the enclosure. So total 27.8 megawatt hours in auxiliary load. And this just shows you now kind of for each month, right? How did these losses stack up? So you see here in red, right, the temperature regulation. You can notice here kind of in the summer months that goes up a good deal. Also in the winter, it goes up as well because, when temperatures get low, you have to kind of heat up your cells to kind of keep them in the OEM range. Right? All right. So we talked about this diagram. Now for the throughput summary here. This section tells you kind of at different points in the project uh, how much throughput you had, while charging and discharging, right? And then gives you some diagrams for kind of daily usage, right? So we provide it in megawatt hours because a lot of OEMs like to use discharge throughput as a metric for performance guarantees. Others like to use cycles. We don't like to use cycles, to be honest with you, because it's somewhat deceptive and it's kind of a two-question parameter, right? You say cycles, the next question is, are you accounting for equivalent cycles or do you mean just full cycles? What type of cycles, right? So energy throughput, I think, is more proper, but we lay out both here. And then, as discussed, kind of the state of charge chart here. Now, we will run a variance, right, in a couple of simulations that will show the effect of the state of charge steering, right? So kind of hang on for that part here. So here, kind of C rate, what was the maximum C rate for both charging and discharging, an average, right? And then the chart to show that. So here, kind of per day, it's 4 parameters: minimum, maximum, average charge C rate, average discharge C rate. And then most importantly, and most impactful to project cost is degradation, right? So we had laid out the project requirements here to have 4 megawatt hours dischargeable at the point of interconnect for 20 years, right? What we have here is we get below that 4 megawatt hour mark at year 6, right? So what does that tell us? We need a bigger battery, right? We need to get to 20 years without going below that 4 megawatt hour mark. We need a bigger beginning of life capacity for our battery system, right? So that's what we'll do here in a bit. And then here we talked about this chart. We see kind of at every point in the project, kind of where our losses are going while the system is discharging and while it is charging as well. All right, so now we can see, yep, less capacity, 2.8 megawatt hours. We're reaching 4 megawatt hours at year 6. We need more batteries. All right, so now let's go back and update our system design to make sure we meet the project requirements. So here you can do the math, right? It is not exact because degradation is not linear. When you increase the size of the system, now the depth of discharge, kind of to the point we were talking about yesterday, Yicheng, the depth of discharge is different. So now when you increase the capacity of the system, yes, you will reach end of life later, and you'll also get less degradation because now it's less depth of discharge you're utilizing, right? So kind of set it to 40 40 racks per inverter, and that gets our battery terminal capacity to 7.5 megawatt hours, right? And now we click run. All right, be sure to save, and let's generate report. Okay, so now we added more batteries, right? We upsized our system, increased the beginning of life capacity. And now here, what we see is we can actually achieve the 4 megawatt hours at end of life, right? Or by year 20. And we were actually targeting, this is something that I probably didn't mention or clarify. We're actually targeting 4.67 megawatt hours because remember the 4 megawatt hours we set as a project requirement is energy dischargeable at the point of interconnect. So you have to account for one-way losses, right, which is about 5%. And you also have to account for a depth of discharge, which is 90% in our case, right?
That's great.
So this is, what's showing here is energy capacity at battery terminals, right? But our project requirement was at dischargeable energy at POI, right? Okay. So when I cycle, if I take this if I take this 4.67 megawatt hours and I have a full battery, right? I need to discharge 90% of that because I can only go up to 95% state of charge and down to 5%, right? I'll I'll have additional about 5% losses one way to the point of interconnect. So that will get me to the 4 megawatt hours. So it's a bit of iterative process because really, I mean, your losses depend on your dispatch, right? And the way you dispatch depends on your losses in a way, because state of charge steering, for example, right? So it's, yeah. All right. Okay. So a bonus here, right? So when we looked at these results, a couple of days ago, we're like, yeah, this is about, a little more than one cycle a day. Is this excessive degradation? What's going on here? Why is this system why are we needing to oversize at 160%, right? Then we did a little bit of digging, right? So we came to this report, we looked at, this chart, and we looked at it and was like, wow, it's all the time kind of reaching the maximum state of charge here, right? Is that causing excess degradation? Yeah, probably so, right? So what we did is, all right, let's assume like a system would be actually operated, right? That, in operation, we will get the state of charge daily to, let's just say 15%, right? So that way, every day we're preparing to charge from solar, right? And we don't have to kind of tune the RTE and the battery profile creator. So let's see what that looks like here, right? So you can do this on your machines as well. Just turn daily state of charge steer on. Any time period really would work that the battery's not already being used at. So 12 to 6 a.m. works. And the state of charge target to make it 10%, 15%, or whatever you deem appropriate, to be more and more realistic to how the system would be actually dispatched, right? If you were operating a system, right, and that you're going to charge, you're probably charge first thing in the morning, probably not going to leave the system here. Like, for example, day 18 here, you're probably not going to start at 45%, right? You're probably going to use that time at night to get to a more suitable state of charge. So here, all right, let's look at the new report, right? Let's look at the state of charge charts. All right, so now, right, every day we're kind of starting at 20%. Every day we're starting at 20%, right? And now we're not hitting kind of the state of charge maximum, and we were able to achieve much less degradation because of this, right? Because batteries generally at lower average states of charge have less degradation, right? So now as we look here, right, we're at 5 megawatt hours at year 20, right? And instead of being at 62% state of health, we're at 68% state of health, right? So, all right, okay, so now I think we're good with kind of the design. So where are we at currently, right? We designed the battery system for case one, which is a solar plus storage project. We know at beginning of life, we need 7.4 megawatt hours. We know we're going to use one inverter. What was it? 4 modules per rack. What was it? 40 racks per inverter, right? So now we can, in a very accurate fashion, develop a financial model for this project, right? Once that is done, we can then start comparing other solutions, right? To try to optimize our system designs as engineers, right? So with that brings us to the conclusion of this first portion